Hello everyone, this is the second lecture on functional analysis. The first lecture on functional analysis is already published in this channel. If you have not watched it, immediately go to the channel and see the lecture 1, and the link of lecture 1 is provided in the description. So now we will start the second lecture. Here in the previous lecture we will know about the definition of a norm, and which are the norm and which not on a space, and also we have already learned that the definition of a Banach space. So in this lecture, Banach space, in the present lecture we will learn about some important theorems on Banach space and about nonlinear space. The first theorem is, it is very simple theorem, but we all have to know this theorem. Let X be a normed linear space. NLS means normed linear space. Then the function x goes to norm x is uniformly continuous. Now proof. Let f of x is equal to norm x, and f is a function from capital X to R. The R is the set of all real numbers. Now here XD is a metric space, where d of xy is equal to norm x minus y, and R d1 is a metric space where d of xy is equal to mod x minus y. Here we have to prove that for every epsilon greater than 0 there exists delta greater than 0 such that d of xy less than delta implies d1 f of x f of y less than epsilon, where x and y belongs to capital X. Now f of x is equal to norm x and f of y is equal to norm y. Now norm x is equal to norm x minus y plus y. We can write it in this way, as if y and y cancel out, then there is only x, that is norm x. This less than equal to norm x minus y plus norm y, by the property of triangle inequality in non-linear space. Therefore, this implies norm x minus norm y, this less than equal to norm x minus y. This is equation 1. Similarly, if we write norm y is equal to norm y minus x plus x, this is less than equal to norm y minus x plus norm x. This equal to norm x minus y plus norm x. Now norm y minus x is equal to norm x minus y. Why? Because norm y minus x is equal to norm minus of x minus y. If we take it as lambda, then we know that in nonlinear space here is a property that norm lambda x or alpha x is equal to mod alpha into norm x. So here alpha is equal to minus 1, that is mod minus 1 into norm x minus y. Mod minus 1 is equal to 1. Therefore, we write it as norm x minus y. This is the reason. Therefore, norm y minus norm x, this less than equal to norm x minus y. This is equation 2. Now, from equation 1 and 2, mod norm x minus norm y less than equal to norm x minus y. Now let delta is equal to epsilon. We take delta is equal to epsilon. Then norm x minus y, this is less than delta, implies mod norm x minus norm y, this is less than equal to norm x minus y, this is less than delta, this equal to epsilon. This implies mod norm x minus norm y less than epsilon. Now norm x is equal to f of x and norm y is equal to f of y. Therefore, we can write mod f of x minus f of y, this less than epsilon. Now mod f of x minus f of y is equal to d1 f of x minus f of y, this is less than epsilon. Therefore, whenever norm x minus y less than delta, this implies norm x minus y is equal to d of xy. This implies d1 f of x minus f of y, this less than epsilon. And this is the required condition for uniformly continuous. Therefore, the function f is uniformly continuous. Theorem is proved. Hope you understand all things. If not, then don't forget to write your doubts in the comments so that I will clear all your doubts. Here there is important definition, that is nowhere dense, nowhere dense. A subset A, capital A, of a metric space. Space is nowhere dense, is nowhere dense if interior of its closure, that is air closure whole interior, is equal to phi. This is the condition for nowhere dense, that is interior of its closure is empty. That is all for today. If you like our lectures, please do like, share and subscribe our channel for more such lectures. Thank you so much.